Yes, I welcome you all for the Automata theory class. So today we'll start with a new module, that is the fourth module. Okay, so we'll start with the first concept, that is a theorem. Okay, pumping lemma theorem for context-free language. Okay, already in the second module you've seen how you are writing the pumping lemma theorem for regular languages. Okay, next we'll see with how we are writing pumping lemma theorem for context free language. Okay, so first we'll see with the statement. So what states that let L be the context free language. Okay, and it is infinite. Okay, next it is containing a string z. It is sufficiently long so that it belongs to language, so that length of the string is greater than or equal to n. Okay, and if the string can be decomposed into substrings, okay, it will be decomposed into 5 substrings: u, v, w, x, y. Okay, u, v, w, x, y. As you see in for the regular languages, you are split into only 3, u, v, w. Here you are splitting into 5, u, v, w, x, y, such that condition is what? V, w, x is less than or equal to n. Okay, so there you have taken what? U, v value is less than or equal to n, and v value should be greater than or equal to n, 1. Here what happens? Instead of u, v, you are having what? V, w, x less than or equal to n, and instead of v, you are having what? V, x value should be greater than or equal to 1. Then u, v raised to I, w, x raised to I, y belongs to L for all the values of I, 0 to n number. Okay, same condition there, what you are written? U, v raised to I, w belongs to L for I greater than or equal to 0. But here you are having what? 5 strings, hence you are having u, v raised to I, w, x raised to I, y belongs to L for I greater than or equal to 0. This statement, store there you are split into 3, here you are split into 5 substrings. Okay, and next, how you can prove that? You are initially assuming that it is a finite language and context free. Okay, then if you want to string z containing of terminals, what happens? We need to apply the series of productions. So case 1 what states that here if you want to have a series of production, one variable should be a recursive variable. So as you written, a implies alpha, a, beta. So here a is what? Recursive variable. If you go on applying this production, what happens? You are getting n number of alpha and n number of beta. So here a is what? Recursive variable. Second one is what? One more is what? Z belongs to L, implies that all the production we get string of terminals. That is the one case. Okay, so we'll see in case number 1 in detail. If you assume that the language is finite and grammar has finite number of variables and of finite length, then we derive the grammar. Okay, assume that initially you are assuming that no language is recursive and each variable defined in terms of terminals. So if you keep on applying the productions, finally we get to the string of terminals, but language is not finite because it is containing more of a variable. We will see in detail how it will be variables. Okay, next, proof for a case 2, what happens? If z belongs to L, sufficiently long terminal, then how you can define? S implies u, a, y. U, how you can define? Again, a is value is nothing but v, a, x. So here, see here, if you take a as a recursive variable, what happens? V, w, x, y you are generating equal to z. So here a value is nothing but what? Vax or w. Okay, so for this, what do we come to know? That every time you go on using substituting recursive variable, v and x value will go on increasing. Okay, so hence what happens? Finally you are having u, v raised to I, w, x raised to I, y belongs to L for all the I values greater than or equal to 0. Okay, so this is the proof of the theorem. First thing is what? You are just generating, you are not, first condition case 1 what happens? No recursive variable, you go on substituting production. Second case is what? There is a recursive variable, so that generate the string of terminals. Okay, so what happens? N is the length of the string and z is decomposed to 5 substrings: u, v, w, x, y, and v, x is present in the z. So u should appear before v and w should be in between v and x. Okay, y should appear after x. Okay, so here your loop value is what? V and x, not w. Okay, but v and x cannot be empty, there should be a value. Okay, if all condition is satisfied, z belongs to, then it is a context free. Okay, so this is the proof of the context free language. Okay, case 1 what states that, again we'll see in detail. So what happens? One variable should be recursive. What happens if you go on applying series of not finite, but you should have one or more recursive variable? That is the first case. And second case proof, what you are having? if you go on substituting, what happens? A is a recursive variable, then v and x should be what? The power should be go on changing, hence v and x will be of a multiple number. Okay, so you can go through this video, and if you have any doubts, we'll have. So this is the theorem once again for context free language. Okay, thank you.